motional EMF. All right, so I want you to think of EMF as voltage. Now the name for this thing is motional force, electromotive force. So electromotive force, and in a sense it makes sense to call this thing force because voltage is kind of like a pressure, but then again pressure is not really a force. So anyways, EMF stands for electromotive force, and motional EMF is, we will consider now, some kind of emotional voltage. In other words, voltage from motion. So I'm going to put here in parentheses, well, this means is delta V from some motion. All right, what we have is this. You take a magnetic field and you make this magnetic field point into the page. So let's draw a bunch of these. So here's the magnetic field, points into the page. And then you take a metal bar. Here's the metal bar. And you make this thing move to the right at speed v. So, well, let's sort of zoom into that bar. Say we could zoom into this bar and we could draw it out like this. This thing just goes on and on and on. But we could zoom so much in that we could see the individual atoms, and so we would have here plus, plus, and plus, plus for the nuclei, and then we would have a bunch of negatives around these, right? If these are metal atoms, then you would have a lot of protons and you'd have a lot of electrons in each single atom, and so I have to put a lot of electrons all over the place around every nucleus. And now you can see that you have this metallic bond where these electrons are more or less evenly symmetrically distributed. Most of them are attached to the nuclei, and some of them will be what we would refer to as the free electrons. So consider this one here in the middle. It seems to sit between these four, this one, this one, this one, and this one, in such a way that it seems to be in equilibrium. Same thing with this guy, same thing with this one, and same thing with this one. And so as opposed to, for example, this one here is bound, this negative here, this electron here is bound to its proton, and so this one won't go anywhere. But this one, this one, this one, and this one, they seem to be more or less in equilibrium, so they may not be attached to any particular nucleus in any strong sense. And so if anything can move here, it would be these four electrons that I drew. So you have these electrons that sit more or less between, symmetrically in the center between the nuclei, and therefore they would be in some sort of equilibrium. So if you could move this one up, if you could somehow manage to move this one up, then perhaps the next one could jump into its place, and this one could jump into its place, this one could jump into its place, and so you end up with some kind of a negative here and some kind of a positive here because this negative has left. You have some kind of a positive here. All right, so so that would be the picture if you were to zoom in. Now, if you take this whole slab of metal and you make it move to the right, speed v, and this thing is sitting in a magnetic field. So here's the magnetic field, and magnetic field is pointing into the page. Then what you have is a bunch of negatives that are free to move, that are pushed through the magnetic field. And that implies that you're going to have a force acting on them. Right? If you have a charge Q that is present in, if you have charge Q present in the magnetic field, and this charge Q is moving at speed v, then there's going to be a force. You will have a force acting on this charge. So let's try to determine the right hand. So we will use the right hand rule to determine the direction of this force. And so I'm going to try to draw it a little differently. So let's try a 3D picture and see if we can draw the right hand, use the right hand rule looking at the 3D picture. So, so here's, well, actually, so here's the metal rod. There it is. And now the magnetic field is, so, and then this rod is moving in this direction. So here's the velocity v, and this thing is just moving in this direction. And then the magnetic field points down at this thing, so it points like this. Magnetic field points like this. Now see if you could, let's see if you could draw this. See if we could draw the right hand rule and determine the direction of the force. So so you would the fingers of your right hand would point down. 3, 4, and then the thumb points in this direction, and you end up with something like this, where if this is the direction of the velocity and this is the direction of the magnetic field, then the force comes out of the palm of your hand, and so the force would be pointing up along the wire in this direction here, where that is at 90 degrees. Let me actually redo this. So let's say that we would have a dashed line here, and then it goes out, force, and 90 degrees right here, and the hand continues on. So the force would have to point in this direction. There's force F, and so if I go back to my picture here, there would be a force that points up like that. But remember that the way I set it up, I use the right hand here. So this is the right hand rule. I use that, and I used it as if it was the positive charge that were to move. But in reality, it's the negative charge that would move. And so what I have to do is I have to specify, I have to say that the force on these negative charges, I'm here, that the force on these negative charges would actually point downwards. So the force would point like this. And that would imply that I would end up with some excess negative charge on the bottom. So I'm going to put here minus, minus, and some lack of negative charge on the bottom, which would imply that this would be plus and plus. In other words, if I look at this wire here, I would have plus on the top, and I'd have minus on the bottom. Which, if you consider the right-hand rule for positive charges, you can think of it that way too. It just means that the force pushes positives up and leaves negatives behind, and that's fine. We know that in reality it's the negative charges that move, but if you use the conventional current, you can think of it as the positive charges moving up and leaving negatives behind. And so what I would have here is some sort of a negative on the bottom and a positive on the top. But if I have a positive in one place and a negative in another place, then I have a potential difference, delta V, between the 2 points. There's a voltage set up there. So this rod, as it moves through this rod here, as it moves in this direction through the magnetic field, will act as a battery, in the sense that it is going to have a positive terminal and a negative terminal. So what I could do is I could then take this rod and I could place it on top of a rail. Let's say we have a rail here that looks like this. Let's see if we could draw this thing. That runs maybe to that point, comes back here, this way, goes, oh, let's see, V is in the way, that's all right. And this comes back. I think there's that, so let's close this off. Here's the rail. Probably add something here. Goes here. It's not bad. Came out pretty decent. This is what we have. And so now this rad here rolls to the right along the rail in the magnetic field. So there's a magnetic field here present. Magnetic field is present everywhere in this space. So it's here, as much as it is also here, present everywhere. But too many arrows will make this too convoluted, so let's get rid of that. All right, now if I put this rad on top of a rail, then see I have a positive, I have a negative here. The charges will flow. I'm going to end up with a current. See if we can make sense out of it. If I have a plus there, then I'm going to have the charges. The force itself causes the positives to move in this direction. So I already have a current that flows like this. And then this current will continue to flow down this way, come this way, and come back to the negative. So I'm going to set up a current. And I could draw this. I could draw this in here by adding I want the black one. I could just put a rail right here. And then what that would do is it would give me a current. See, the force F here is pushing the charges already up, conventional current, so the charges already flow in this direction. And then they'll simply, well, they can't just, if there was no rail, they would just pile up on the top here. But because there's a rail, they have somewhere to go, and so they'll go into that rail, and then likewise, so this is the flow of the current. And here on the bottom, as the positives recede, the charges from the wire are attracted, and so they will flow into it. I'm going to have this current here that loops all the way around. So I can generate electricity. So it's not a very efficient way of generating electricity, but I can generate electricity. I can take a rad, throw it through a magnetic field, and that rad will act like a battery. So there is an equation, we'll have to derive it, but there is an equation for the voltage in the voltage set up here between the two ends of the rad. So I have this voltage here, delta V, is what we call EMF, electromotive force, and that thing is equal to V times B times L, where L is the length of the rad. So I'm going to box this off. And this here, V is the speed of the metal rad. This has to be in meters per second. B is the magnetic field. This is the magnetic field, and this is Teslas. L is the length of the rad, and that's just in meters. All right, so I think this will do, but I'm just going to briefly derive that expression. If you follow it, great. If you don't, you'll live without it. But anyways, what we have here is so we have pluses on one side, minus charges on the other side of the rad, and so I have here some kind of a Q. I have some kind of a Q. One is plus, one is minus. It takes a certain amount of work done by force F present in this to move the positive charges, and that would just be F times L, where by L I mean the length of this whole thing, and then times the cosine of 0, because F points in the same direction as L. But the work done by force F is also equal to the potential energy set up between the two charges, and so that would be that potential energy between the two charges is just Q times delta V. That equals F times L, and so now what I have is voltage equals F times L over Q. But the force, this is a magnetic force produced by a magnetic field and the charges that move through the magnetic field, and so that's QVB. there's a sign here, but it's the sign between sine of some alpha, but this alpha is the angle between V and B, and so that's 90. So I end up here with delta V equals Q V B L over Q. That goes away, and I have the expression I wanted. So delta V equals V B L. All right, so these are the concepts. Actually, there's more to the concept. So anyways, here's the equation. So we have the equation, but now let's look at couple different options in terms of the direction of the current. Let me draw a few things. So here's a magnetic field that points into the page, and here's the region where a magnetic field points out of the page. And now let's set up a few different things. So let's say that we have a rail here that looks like this, and that we put a rod on top of it, and we make it move in this direction at velocity v. Try to determine the direction of the current in this loop. And then likewise, suppose that you have a track that looks like this, and then you place a rod over it and make it move in this direction at velocity v. Try to determine the direction of the current in this section. And then here, let's say we have the following setup, and then here's the rod, metal rod, and it moves at velocity v. Try to determine the direction of the current in this little loop, and then maybe we'll do one more where we have a track that looks like this, and then here's the rod, and the rod is moving in this direction, velocity v. And the goal here is to determine direction of current I in every single case. So so you should try by yourself, pause the video, and then play it again. Let's start with this one. So consider right-hand rule, the right-hand rule for each case, where you're looking at the force acting on a positive charge as it moves with the rod. So within this rod, you have positive charges. I'm going to draw these positive charges. Here's a plus, here's a plus, here's a plus. In reality, we know it's the electrons that move, but it doesn't really matter. It comes out to be the same in the end. And so here you have these positives which are in this rod, and this rod is moving. As the rod moves to the left, so do the positive charges move with it. And therefore, there's going to be a force on these positive charges. So use the right-hand rule to determine that. The hands of the fingers of your right hand should point into the screen because the magnetic field points into the screen, and then the thumb should point. The thumb of your right hand should point to the left in the direction of velocity, and then you will see that the force moves down. The force points down. The force acting on each one of these here going to point in this direction. This is the direction of the force, and that implies that these charges will have to move. Now, when they can't just jump into the air. I suppose they could if there was enough of force, but they won't really move into the air because they can easily flow into this section here of the wire. So they'll do that. They'll flow this way, and then they'll come back around. They're going to have the current that flows like this. For the bottom one, same story. That is, take your right hand, make your fingers of your right hand point into the screen, and then rotate your hand so that the thumb of your right hand points in the direction of the velocity vector, and then you will see that forces acting on these charges point. The force acting on these charges points in this direction. So this is F, and that implies that these charges will move to the left, and instead of jumping into the air, they'll move into this section, and then they'll loop around, come back, and now you have the direction of the current, I. All right, let's determine this one here. So now what we have is the magnetic field points out of the page, and so you have to take your right hand make the fingers of your right hand point at your face. Rotate your hand so that the thumb of your right hand points along the velocity vector, and if you do that, then you will find out that the force acting on these positive charges here points to the left. Let's make sure that that actually is true. Yeah. Right, and so that means that the charges will move into this little section. They'll flow like this, and this will be the direction of the current I. And then finally the last one here. So take the right hand, make the fingers of your right hand point towards your face, and then rotate your hand such that the thumb of your right hand points in the direction of the velocity vector. That would imply that the force acting on these positive charges here is pointing down, force F, and that would imply that these charges here will move into this section. They'll loop around, come back, and this will be the direction of the current I. For this, all of these I's are a conventional current. This is always a conventional current. All right, so that does it. Oh, maybe one more thing is, now you have the expression for the voltage set up between the ends of the wire. We call this electromotive force EMF. That's VLB. And you know how to determine the direction of the current, and then I equals delta V over R is the equation that would combine voltage with the current, where R would be the resistance of your loop. So R would be the resistance of the loop. Okay, so I think in the next video I'll solve one simple problem with this.